Okay, so moving on to the next talk. So it's my pleasure to introduce Victor Prisacariu, who I think it was 2 years ago that I had the pleasure of working with him at Oxford for my postdoc. So a few words about Victor. So he got his PhD at the Activision Lab in Oxford, where he focused on methods for using priors in 3D reconstruction and tracking of objects. After spending some time as a postdoc, he became an associate professor at the University of Oxford, where he co-leads the AVL. Also, he co-founded 6D AI, where he was a chief scientist, where the startup worked on things related to the AR cloud, such as large-scale mapping and localization. And after the recent acquisition of 6D from Niantic, he's now a chief scientist at Niantic. So welcome, Victor.
Well, thank you very much for the intro. I'll share my screen now with the slides. Is everything visible properly? Just to double check.
Yes.
Yes, it works.
So hello everyone, I'm Victor, as Vasily says, and I'll be talking about some of the work we've done, mostly in the lab, on correspondence networks for matching and relocalization. One way of doing relocalization with correspondences, and there are many others, but one way to do it is to say that you have some sort of database of frames that you've built a priori, you've been somewhere, you filmed around, and then you have a new query image. And you have some magical way of finding the closest image from your database to that query image, where closest is something we would define somehow. And once you have the image pair, you pipe them through some sort of feature extraction, feature matching, and then you take the matches and you use them to give you a pose. Correspondence networks take the two blobs in the middle, namely the feature extraction, feature matching stage, and capture them as a neural network. Both the feature extraction and the feature matching will be dense. What this means is that I will extract a feature for potentially every pixel in the image, and then I will match every feature that I've extracted from one image with every feature that I've extracted from the other. The original approach for using neural nets for this sort of correspondence networks was ANC-Net, Neighbourhood Consensus Network, and it looked or worked something like this. So you'd use a neural network to extract dense features from your input images. Then you would take these features and build them up into a correlation tensor C. And this is a rather big one because it's a 4D correlation tensor, which is something like width by height of image 1 times width by height of image 2. And at each location, you're going to have the probability of that specific match being valid. Then you would pipe this correlation tensor through your magical neighborhood consensus network, and you'd get a filtered tensor at the end. And if you were to take the points of maximum probability or maximum value within this tensor, you would get the actual matches. Another important thing here, another interesting thing, is that this was trained in a sort of very weakly supervised way by just using positive and negative pairs of images. Now, the first work that I'll be talking about today is one that we have in the CVPR. It's called the ANC-Net, and aims at tackling sort of three potential, I don't want to call them problems, but the three potential improvements on ANC-Net. First one is multiple matching candidates. You might end up with, or in many cases, a certain point will match to multiple points in your target image. You're going to have a scale or a viewpoint difference between your target, your source, and your target images. And ideally, especially when you look at SLAM, you would probably want to have the ability to do slightly more informed training. So ideally, you would use something that you can extract easily and automatically from the images, such as, say, sparse point matches. So let's start with the first part. Let's look at the standard sort of approach, ANC-Net. What this one does was that you take your two images, you extract features, and use cosine correlation to build your correlation tensor. One of the things we added was another pipeline that works the same way as the feature pipeline, but this time encodes self-similarity. So we take the features, say the features from the source image and the feature from the target image, and we build SS and ST, the self-similarity features. And then these go through the same sort of correlation, cosine correlation, and build our target correlation tensor, but now in terms of similarity. The self-similarity module looks sort of like this. So you take, for each point in your feature map, you take the points around it, locations around it, you compute the cosine distance, and then you put all of these into your coarse level or self-similarity as 0. And then you do 2 more convolutions to distribute context a bit more, and you concatenate them all into a single feature S here. Once you have both of these correlation tensors, CF and CS, so one built for features and the other one built for the self-similarity, you can add them up, and then you pipe them through the adaptive neighborhood consensus, our equivalent to the ANC-Net. ANC-Net was sort of worked like you see on the left here, so it was a rather simple collection of 5 by 5 by 5 by 5. These are 4D convolutions. What we've added is another pathway through this network that uses non-isotropic kernels, so 3 by 3 by 5 by 5. The whole point here is to add a bit of robustness to the scale difference between the 2 images. Finally, the more interesting bits is how would we train this? Previous methods like ANC-Net trained using weak supervision, so positive and negative images. Ours is also weak, but is less weak. So we're using matched key points. If these are semantic classes, you'd have to manually label them. These would be like the various parts of birds from one of the more famous data sets. But in a relocalization scenario, these would be feature points from the structure for motion or SLAM that you'd be able to project into the corresponding 2 images. Now, the loss has 2 aims in our case. The first one is that we want the peaks in our correlation tensor to actually project to key point location in the 2 images, S and T. So if you have a point of high probability in your correlation, that should correspond to feature location or to high probability of being meaningful points in your pair of Z images. The other thing we would care about our loss is that we should only have at most a 1-to-1 match. So each final feature point from one image should correspond to at most 1 feature point from the other image. It might correspond to no feature points because that specific part of the image might have disappeared, but you do want to have at most 1 match. So when you build the loss, it looks sort of like this. The key component here is the matrix M, and this is very simple. It is just a slice through your correlation tensor, where you've taken the specific slices that correspond to your key points. And then the final loss has 2 components. One is looking at making sure that the positions of the maximas in your correlation tensor match the locations of the key points in the image. And the other one is what we call the orthogonal loss, and this comes from or is inspired by graph matching, and this aims at encouraging uniqueness. A few results. You see on the left is the result for dense matching. And you see the source image, for example, the top you have a Renault and a Mustang there, and you see that ANC-Net does a good job, but ANC, at least in this case, tends to look probably a bit more realistic. I mean, neither of them really looks realistic, but ANC tends to look a bit more like you'd expect. And the same for the dog and for the couch. On the right, you see an example of sparse key point matching. So here we want to match the leg of one dog with the leg of a different type of dog. In green, you see the ground truth, and in red, you see the prediction of the method. So you see that we take the green from one, and our method does well. The other ones do fine, but not as well. Now, obviously, anyone can find pretty pictures to show results for, but we're also doing reasonably well quantitatively. So we're able to get effectively state-of-the-art data results on the approaches that existed at the time of submission. So this approach, the ANC, basically looks at dense correspondence estimation, and it's trained with sparse key points. And it works well because of those 3, or collection, I'm going to call them hacks, but collection of net changes to the network. But what about relocalization? Well, ANC-Net, as it is, uses a lot of memory. Uses much more memory than ANC-Net because it creates a separate pathway, and it effectively doubles the amount of the size of the correlation tensor because it uses the one for self-similarity. So when we actually started to use this for localization, we saw that we were only able to fit small images in our GPU. So there wasn't enough RAM to fit big images. And this was before sparse ANC-Net, which is another approach, was introduced. And interestingly enough, we found that the higher resolution the feature map, the better results you get for relocalization. So for example, to get state of the art at the time in relocalization data sets, ANC-Net would use an input of 3200 by 2400, and this would generate a small feature map of 200 by 150. ANC-Net would have been using the same type of input, but would have needed even more memory. So the second approach I'll quickly walk you through today is dual RC-Net. And this is a network architecture that aims at outputting higher resolution feature map with hopefully as large GPU requirements as if you weren't as ANC-Net. And it works effectively by adapting the feature pyramid concept both to the features, as people have done before many times, but also to the extraction of the correlation tensor. And the way it works is that we start with a standard feature extractor backbone, sort of like that, and then we run ANC-Net on the coarses resolution of the features. You could also use ANC or any one of your favorite approaches for correspondence. There are a few others that I didn't mention here, such as parse ANC-Net, for example. At the same time, we're also going through a feature pyramid, a network that extracts or builds high-resolution features, as shown in the middle of this slide in blue. And this is why we're calling this a dual resolution feature generation. The next step is to then figure out what are the points in the low-resolution correlation tensor that are likely to be good matches. So you only select the ones with high scores, and then we only upload the ones with high scores. And then similarly, for the location of high scores, we're also building score maps. But we're building these ones from the higher resolution feature maps built by the feature pyramid network. So what we end up at the end is with two correlation tensors, or two sets of slices through the correlation tensor, one coming as a simple upsample from the original ANC-Net, and the one being computed from the high resolution feature generation. And then you multiply these, and that is your final output. It's a rather simple approach, but it turns out that it works really well. So here is on a few results on Inloc, and we are able to, we were getting state of the art on this, including when compared to sparse ANC-Net, which is an approach that I think is 2 months old, which popped up after we had started work on this, and we're still getting good results. Of course, no paper would be complete without us trying to sort of shame the authors of the state of the art. Obviously, there are very good results in both sparse ANC-Net and ours, but here are a few examples where ours behaves better. Similarly, we look at the Aachen day and night data set, and here we get competitive results. We're as good as sparse ANC-Net in some cases, or better than sparse ANC-Net in some cases, or good as sparse ANC-Net in some other cases. And as before, we are able to generate nice-looking matches. Some conclusions on dual RC-Net. Feature size, or feature image size at least, matters. And you can take these sort of coarse-defined approaches that you've done in feature pyramid networks and adapt them to the same sort of correlation network, and it gives you very good results. So, and this sort of the first sort of chunk of my presentation, I showed you sort of two approaches for getting state-of-the-art-ish results for feature correspondences, ANC-Net and dual RC-Net. ANC-Net combined the various tricks and hacks to get better results, whereas dual RC-Net just aimed to increase the resolution of the match. But both of these methods are not very quick. They both take a few seconds on a good GPU. And even sparse RC-Net is still looking, a sparse ANC-Net, which is sort of a simplified version of ANC-Net, also looks at 1 or 2 seconds on a GPU. So how can we take these methods and apply them sort of in a more scenario where Niantic is interested, as in things that run on mobile phones? Well, we can do similar stuff. I won't exactly explain how that works, sadly, but I will show you a few videos and demos. So here's an example that some of you might have already seen. The video is, here we have a mobile phone, and I'm moving around the Department of Engineering Science here, and I'm building a depth image. So this is entirely monocular, and is building a depth at each frame. It takes about 15 milliseconds per frame. And you see that it is able to obtain, let me scroll back a bit to here. It is able to obtain sort of nice reconstruction of the space. Then I can walk around a bit more, and I'm able to build another reconstruction. So I can just commit to the same, and I can actually go all the way and close the loop in this case, both indoors and outdoors. And I've built a nice dense map, again, entirely on a mobile phone. But the demo that I haven't shown much so far is that we can also use this for relocalization. So you can upload it to the cloud, and you can download it to the device, and then you can relocalize in it. So, and you can also see annotations that people have done on that specific map. So here I'm walking to a map that I've uploaded before. I'm relocalizing relative to that map, and I can show the position of the mobile phone in that specific map. And now, and hopefully I have, yes, I still have a few minutes. I will try to demo this. And this is the first time I do a public demo over Zoom, but hopefully this will actually work. So I will stop my screen share of this, and I will instead share my mobile phone. So here I have my mobile phone. I am hopefully, yes, hopefully everyone can see my mobile phone. That's my kid. You're going to see his toys soon. So we can start with the first build that I showed you, how to build a map. So here's, you see the live stream on the phone, and I can move around, and I'm reconstructing live, and I'm building a 3D map. I'm going to walk to the other side of my house. Excuse the mess, but when you have a 4-year-old in the house, things are not entirely stable. Neither are his parents after a while. So I'm able to build this reconstruction. I can tidy it up a bit. This is the sort of reconstruction I was able to build. And this is nice, but it's a bit nicer if we can use it for relocalization. So here I'm starting the other app, the relocalization demo app. And I am going to create a new reconstruction of this, and I'm going to call this CVPR 20. And I'm going to scan. So here I'm doing the same. The child is about to come barging on. I'm doing the same sort of reconstruction I did before. And it's in there. And I'm uploading it to the cloud. It's piping it through the cloud mostly for cleaning up textures. So now it's doing some texture cleanup on the cloud. It's getting it done. It takes about 14. You see on the screen share, it takes about 11 seconds. I'm waiting for this to finish. Okay, so now after this is done, it's going to download it from the cloud. And you see sort of, it's a much smaller reconstruction than I did before, but it's sort of see it looks. And I can put a note here somewhere. Let's move this note so that it looks like it's sort of on top of the couch here. And I can relocalize. So now it's going to download the data that I'm using for relocalization. And then I relocalize. So this entire localization ran on device, and I did it live right now. I can do another one. And the symbol is still there. Another one. Let's try this one. All right. It usually runs like it. Now, another fun thing you can do with an AR cloud is to share your map and should give it to other people. So what I'll do is another phone. And now I will stop sharing from this phone. And I will start sharing from my other, from my other phone. And that's my other phone. So now I'm going back to my map, and I am sharing it to my other mobile phone. So now the map was shared through magical Apple, as it takes a second for it to pop up. It's updating, and now I'm downloading the same map. And if all goes well, after the rather slow download, I should be able to relocalize in the same world. Apologize for the speed of my internet. So that's the same map as before, and we can see the node. And now we can relocalize. And it's there. Another fun thing we can do, let's see, hopefully this works, is I'm going to relocalize with the other device. I'm going to put it there. And I don't know if this will work very well. Okay, let me put it there. So I still have my other device, and it's there. So I can go and see where it is. And all of this is sort of transmitted live on the device. Anyway, enough with the demos. The same sort of, oh yeah, thank you very much for appreciating the cleanliness. This is running the same sort of approaches as the sort of stuff I showed before, but optimized in different ways because you need to run these on device. Well, thank you very much. Magically, I was a bit quicker than I expected.
Thanks, Victor. So this is a virtual clap. So yeah, first of all, we have people claiming that it's not that messy for your house, and a lot of impressed comments about the demo. So yeah, if anyone has questions, there's a bit of a delay due to the YouTube stream, so I can start with one. So you said that these things are based on the same methods. You somehow try to make them faster to.
Yes, I will. So the one thing I can say is that they're both using neural nets and they're both using concepts related to the stuff I presented before, but simplified in a way that will run in 100 milliseconds on a mobile phone.
Okay, yeah, that's yeah, because normally when you have things like 4D correlation maps, or you have two big feature maps and then you try to match everything with everything, it becomes very messy, I guess. At some
Do you really have to match everything to everything? That's
actually related to something else I want to ask. So you said you want to enforce either 0 or 1 in terms of it has to match at most 1, or it doesn't match at all, right?
Yeah.
So how do you? There are probably many ways to do the 0 when you don't have any match, because you might have two completely different images, or you might have an image that is included by something else. Let's say, is there any difference between these two approaches, or is it the same?
If you were to force a 1-to-1 match, you would just say M times M transpose minus identity equals to 0. So that would say that I have to have at least when I'm matching something against itself, I will have to have a 1-on-1 match. So you'd end up with an identity there. Now, if you say that some of those can be 0, then suddenly you're allowing it to match to nothing. So if you do M transpose minus M transpose with the ground truth, then you're basically saying I want the sort of self-correlation to be the same in between ground truth and non-ground truth, which means I should only have at most one sort of self-correlated. No point should correlate with others. That's basically what you're saying, or have 0.
Yeah. Yeah. Okay, so we have a question from the YouTube stream, which what are the privacy implications of this sort of system that you saw now?
It's complicated. We're spending a lot of effort making sure that, or making sure, again, a strong word. We're doing our best to send stuff that is not, that doesn't violate privacy, because this is running through proprietary neural nets that have had some effort to keep private. We're hoping that this will hopefully alleviate some of the privacy concerns. That being said, as it is, all the demos that I'm showing assume that everything is public. And of course, this will change at some point if this was to be developed further, but I cannot speak for the company on this.
Okay. Yeah. Next question is, have you seen Magic Leap's CVPR 2020 superglue? Because it's similar ideas, feature matching, and they also have a demo. So how do you think it compares with the machine learning based feature matching you were showing?
Oh, we didn't compare. We compared with the SuperPixel. So before the superglue one, and we were drastically better, but I've seen them improving it a lot. So I think it's actually an interesting thing that we should compare against.
They were probably submitted at the same time, I guess, because
exactly. So when we were comparing with the super points, it was certainly better, but the superglue it might be.
Okay, next is, can you talk a bit about the scalability of the system? How much latency comes up with the increasing map size?
So it ends up borderline to, it goes up to a fixed amount and doesn't increase past that. The current tests show that we can run relocalization within 100 milliseconds on device. I don't want to say regardless of the size of the map, but with something the size of my house, it'll be within 100 milliseconds. After that, you have to do other tricks and hacks, which I can't comment on. But I would certainly hope that the ultimate aim is for it to always run within 100 milliseconds for a relocalization attempt. Whether that will actually be achieved in product, God only knows. But as it stands, we're sort of aiming for that.
Okay. Yeah, we have time, I think, for a couple of more, if you also have the time.
That's fine, sure.
How do you deal with textureless areas with this kind of system, like white walls and occlusions around the object boundaries?
So one thing I can say about relocalizer there is it's not just 3D to 2D. So it would also look at 3D to 3D matches. So as long as you have some version of a surface there, you're likely to be able to relocalize. Now, if you don't have any surface at all in the reconstruction, and that can happen, then you'll be in trouble. But as long as you have some sort of surface, it would still work. You've seen the sort of Kinect style relocalizers that are able to relocalize even if there's nothing there.
Yeah. So I think the next question is related. What are the failure cases of the network? So
the biggest problems, I would argue, are still sort of day-to-night transitions. So when stuff doesn't look the same, and that means that obviously you can do things, you can build up the ways of compensating for this, but at some point things will just not look the same. You might have built your map now, and you're coming back a month from now, and at night. So the images are going to look different. The 3D is going to look vastly different. And we're doing some interesting work in the lab that will hopefully be published, first submitted and then accepted. That is looking at eliminating as much as possible the influence of furniture and of everything that can be dynamic and still being able to relocalize. But I would say that's the main limitation, is that the world changes, and it is more susceptible to change than a human would be.
Okay, for running on mobile, I expect the train model would be light. Do you have any suggestions for keeping the models light on mobiles? Someone is asking from YouTube. Any generic tip?
So if you look at some of our other papers, I tend to like quantization. We've had a paper in last year's ICCV on quantization that showed good result. It was called DSConv. I also like the typical sort of mobile things, and we have some papers in ECCV which may or may not get in on training network architectures and looking at varying group size. This one's on archive, so you can tweak group sizes. You can optimize. So depth-wise is great, for example, for making mobile inference quick. But you can also improve accuracy by using group conv, and this is a paper that is on archive now and may get in ECCV. Yeah. So I don't know of any sort of magic bullet for this, but I do like stuff like the network architecture searches from Facebook, for example, FBNet, and the sort of quantization that would get stuff running quickly. But most of the time, I think the most important thing is custom code and common sense. If you're building your code for your specific application, you're able to extract a lot of benefit. But if you're going to try and make it generic for everything, it'll be slower.
So it's a mix of quantization, custom architectures, and custom code.
Yes. Yeah. These demos use entirely our own neural network pipeline with everything is implemented by hand.
Okay. Yeah. Next question is there are three different systems: standard mobile phones, then the iPad with a new LiDAR depth sensor, and full-fledged AR systems like HoloLens or Magic Leap glasses. How does your system USO compare with these systems?
So our system, as I said, one of the things that it uses is the sort of 3D to 3D relocalization, which means that the moment you give it a good depth image, it will behave even better. So it's in a way compatible with all three. You can have a headset that gives you a depth image and you can relocalize. I can't give examples, but back in N60 days, we In fact, I can't give example because it was public. Back in 60 days, we had a collaboration with Qualcomm where we were able to localize the headset from Nreal to the reconstruction map built on a mobile phone. So I would say in an ideal scenario, you would want a system that is compatible with all three. So you want to relocalize your phone in the map built by Magic Leap or in the map built by an iPhone. So you want all of that to work. So you have to worry about compatibility, even across mobile devices. One of the important things of our system was that so first of all, it worked between two different phones, and it actually works between two different phones, a different type of different capability, and that's something that doesn't just naturally happen. So as long as you're aware of this and you work towards it, ideally you would end up with a system that unifies all three.
Okay, yeah. Next question is, how do you deal with bad mappers? For example, if the map was built by someone inexperienced without good multi-view paths, I guess, or tracks, is there any magic trick there, or you just cannot build them?
I would say that's more of a work style. There's more of a style of development that you should do. One of our main aims is to make our life as hard as possible. So we've always tried everything we test on to be as realistic as possible. And I mean, sadly, some of it is still filmed by a computer vision scientist. So I think, unconsciously they're going to hold the hand straight. But we're certainly doing our best to make the videos as hard as possible. So it is something that you have to do when you're building a system like this. You have to ensure or assume that the person filming will not have a PhD in computer vision. So we're now how to actually solve for that. That ends up being robustness in the training and neural nets. That ends up being having robustness in the sort of computer vision component. But I would think it's much more important to assume that you will have to solve it and not make your life easier by filming all the videos yourself. So it starts with making sure that you're using the correct video to test on.
Yeah, I think there are no more questions, so I can say again that
I actually have a question.
Yeah.
I very much like your comment. Great talk, first of all. Very much enjoyed it. Thanks for using our data sets, by the way. I liked your comment about robustness and not being able to rely on having someone with a PhD to take the data sets. So are you planning to make some of the data that you capture available for other researchers to actually get this effect?
So from my personal point of view, and this is in no way, from my personal point of view as an Oxford associate professor, yes. But this ends up being a company decision, so it's not something I can speak for. But I would really like to.
Cool. Yeah, that would be nice. Thank you very much.
Okay. Thank you again.
Okay.